In this video, I'm going to explain how we can use Thomas method to solve the system of equation that we got from Crank-Nicholson approach. If you recall from last video, we actually came up with the system of equations where we had u's on the left and then v's on the right. So remember, u's were the j plus 1 variables, and then v's were j variables when we just plugged in j equals 0. So this system is only when you get j equals 0. We haven't talked about when j is equal to 1, 2, 3, and so forth. All right, so this is only about j0. After we solve this system, we're going to see how we can generalize this to get the variables for other j variables. All right, so let's go over one of these equations one more time. The first equation we had was negative u is 0 plus 2 times 1 plus del x squared over del t times u1 minus u2 is equal to v0 minus 2 times 1 minus del x squared over del t times v1 plus v2. And so we saw that if we increase I or increment I by 1, you're going to increment all these subindices by 1. So u0 becomes u1, u1 becomes u2, and so forth. We also discussed that the last equation we get is when you plug in I equal n. So when you plug in I equal n to this general equation where j was 0, basically you're going to generate some n plus 1 variables. Look at here. If I is n, you're going to see wn plus 1, which now becomes vn plus 1. And on the left side, wi plus 1 comma 1 becomes un plus 1. So you're going to see n plus 1 variable when you plug I equal n. All right, so I hope this is not confusing. I'm going to plug I equal n here, but you're going to see un plus 1, un and un minus 1 in the last equation. So let's go back to there. So this is the last equation when I plugged in I equal 1. I equal n. And so you get negative un minus 1 plus 2 times 1 plus del x squared del t un plus 1, and on the right side you get vn minus 1, vn, and vn plus 1. So now this looks a bit messy. Let's redefine the coefficients. I'm going to keep all the u's and v's, but I'm going to rename the coefficients to c, d, and e's. Like in the first equation where I plugged in I equal 1, I'm going to rename the coefficients to c1. This whole thing becomes d1. This negative 1 becomes e1. All on the right, I'm going to call it b1. The second equation, I'm going to call all variables as subindex 2. So this one becomes c2. This whole coefficient becomes d2. This negative 1 becomes e2. All on the right becomes b2. Okay, so you can do the same thing with this third equation. You get b3 on the right, and then this one would be e3, d3, and c3. If you agree with me, then the last equation become, this one is cn, I'm sorry, the negative one is cn, the coefficient only. The coefficient is here dn, 2 times 1 plus del x squared over del t. And then this negative 1 is actually en. All right, so cn, dn, en, and everything on the right is bn. Again, these have n subindex because that's the nth equation. That is why, or where I put I equal n. Okay, so let's stop here and then just discuss Thomas method. Thomas method is a method to solve a system of equations where we have only 3 diagonals. Look at this equation for a minute. This is a system of equation where I have a coefficient matrix over here, unknowns here, and these are the right side, which are known. I have n equations, and the coefficients are like this. On the diagonal, I get d's, d1, d2, d3, dn. And I have 2 off diagonals. This is the super diagonal, starts from en to en minus 1, and then the subdiagonals start from C2 to Cn. So this is very important. The diagonals are from 1 to n. Off diagonals, the super diagonal is from 1 to n minus 1, and then the subdiagonal is from 2 to n. In other words, the subdiagonal and super diagonal have only n minus 1 elements, but the diagonal has n elements. That's how you can get an n by n equation. So this is an n by n system. Everything else are 0. Unknowns are from 1 to n because we have n equations, and right side are b1 to bn. So this is the general form of a Thomas method. If we have this system, we can use the script in the text, which is written in VBA, to solve this system in Excel. If the system is different from this, you cannot solve it by just using the Thomas method. You have to modify the Thomas method in the text. But if you have n equations with these coefficients, basically d1 to dn, c2 to cn, and e1 to en minus 1, you can use exactly same Thomas method without having any modification. So now the question is how we can solve the system we have up here using Thomas method. There are two problems. The first one is, in the first equation I have C1, but if you look at the Thomas method, there is no C1 in here. The first equation starts from D1 and then E1. There's no C1 here. So that's one problem. I have C1 in the first equation. The second problem is in the last equation, I have the coefficient for un plus 1, which is actually En, right? This is En. But if you look at the Thomas method matrix here, I do not have En. I have Cn, Dn, but En is missing. So I need to get rid of En here and get rid of C1 there. There are two things you have to get rid of to be able to solve this system using Thomas method. Well, fortunately, most of the time, U0 is known. U0 is basically, if you look at this picture, U0 is the boundary condition on the left. So U0 is known. If U0 is known, you can actually take the whole UN with the coefficient all the way to the right side. So then your B1 now includes negative U0. So basically, you don't need to include this in the first equation. This actually goes and gets absorbed in the coefficient B1. So that is to solve the first problem. Okay, so there's no U0 here anymore. It's going to go to the right. How about UN plus 1? Well, this is still unknown. I don't know the boundary value on the boundary on the right boundary. So in the problem set 7, the question that you're going to solve is apply this boundary condition on the right, du dx at x equal 1 equals 0. So let's discretize this using backward difference. Well, you have to use backward difference. You cannot use central difference because that is a boundary point. Let's look at that. And the boundary point, you do not have anything on the right side, so you cannot do central differencing. Otherwise, you're going to see n plus 2 in your equation. That's why we're going to use backward difference using un and un minus 1, right? So if you discretize this using backward difference, you're going to see 3un plus 1 minus 4un plus un minus 1 divided by 2 del x equals 0. You can actually see this by looking at page 83 of the text. That is the second order approximation to the first derivative. Okay, one more time. That is the second order approximation to the first derivative. I actually put that at x equal 1. Now, if this is 0, upstairs or the numerator has to be 0. So you set the numerator equal to 0. You can solve for un plus 1 from here. So then un plus 1 becomes 4/3 un minus 1/3 un minus 1. So how we can use this now? Well, look at the last equation here. Recall that this is an extra coefficient. I cannot have this if I want to use Thomas method. So to get rid of this term, I'm going to use equation 2 here and then plug that in to equation 1. So what do I get in that case? Well, so let's look at that more carefully. If I plug this un plus 1 into the last equation, that means basically if I cast my last equation in terms of C's and D's and B's, so let's look at that one more time. So this is basically nothing but Cn minus 1 dn minus un plus 1 is equal to bn. That is all I have here. Okay, so there's nothing changed yet. Now, I'm going to use equation 2 and replace un plus 1 with this right-hand side. So all I get now is Cn un minus 1 dn minus, instead of this, I'm going to have 4/3 un minus 1/3 un minus 1. Okay, this is equal to bn. The right side hasn't changed. Now I have un here and un there. Also, un minus 1 here, un minus 1 there. So let's group these two and group these two. All I get is Cn plus 1 plus 1/3, the contribution from this term, times un minus 1 plus dn from here, negative 4/3 from there. You get dn minus 1 minus 4/3 un, this is equal to bn. So let's call this C prime n and D prime n. All I did so far is I rewrote this last equation in this form, where I have only un minus 1 and un. I do not have un plus 1 anymore. So if you look at this equation and replace equation 1 by that, by equation 2, by this equation, then now you can use actually Thomas method, because then you do not get the coefficient en anymore. So all you have is Cn prime here and Dn prime there. This is Cn prime and Dn prime. So I can recast this whole system like so. So from equation 1 to n minus 1, nothing has changed except the last one. Instead of having Cn dn, I have Cn prime and Dn prime. And note that I got rid of un plus 1 variable. So I do not have un plus 1 anymore. Now, this system can be solved using Thomas method, because there's no C1 here and there's no En there. This is pretty much exactly what I needed. N variables on the diagonal, n minus 1 on the off diagonals. So that is the trick of using the boundary condition to get rid of un plus 1. Okay? So all you need to do now, you go to Thomas method and change the coefficient Cn and Dn to whatever Cn was plus 1/3 and Dn minus 4/3. So in the next video, I'm going to show you how you can modify the script to implement this change. Thank you so much for watching.